Hello everyone and welcome to another stream with myself, Luciano, and
Roberto. Yeah.
So in this channel, what we do is basically solving advent of code challenges in Rust, because our real objective is actually to learn Rust. So if you never did Advent of Code is basically challenge that happens every year in the Advent period, so around before Christmas. And basically those are coding challenges with an interesting backstory. So you're kind of solving coding challenges, but also progressing through the storyline. And if you want to check it out, you can find it at adventofcode.com. We are doing the exercises from the year 2020, so last year, and we are publishing everything in our repository, which you can find here. If you want to see the previous episode, all the recordings are available on YouTube. If you are already watching this on YouTube, we'll live stream on Twitch, so make sure to find all the links. They are generally in the description of the video on YouTube, or if you are on Twitch, you can find it in the information box. So with all of that being said, what we did last time was the exercise number 14, part 1, and today we want to work on the second part. But before we move on to the second part, we did some changes on part 1. So I want to show a PR that basically illustrates some of the changes that we wanted to apply. If I can share my screen. There. So you should be able to see my screen now, and you should see the PR, right, Roberto? Do you see my PR?
Yes. Yeah. Let me remove the banner. Okay, yeah, so we have more.
Perfect. So let's go to the code difference. So the first interesting code difference is that we tried to remove allocations. So we try to use str rather than using a string. And the reason why we did that is because at the end of the day, our input is a big string that is embedded in our tests. So it's a big str already in memory. So it doesn't make a lot of sense to just read line by line and create instructions and reallocate parts of those strings, when at the end of the day, we can just have slices over the original string. So this is the way we are accomplishing that. And the interesting thing in Rust that we are always a little bit afraid of is that when you use references in an enum or a struct, you need to start to specify lifetimes. And here, what we are doing with this syntax is basically we are making our instruction enum generic over a lifetime that we are calling A. So in reality, since our string is going to be embedded in the binary, this is going to be a static one, but declaring this way basically makes it generic over any type of lifetime. So this was the first change. And of course, when you do that, also the implementation needs to be aware of that specific lifetime. So here we needed to change a generic implementation for our from string, and we made it with all these things. Now, this was interesting because if you look very carefully, you'll notice that we actually are implementing now a different trait. We are not implementing from string anymore, but we are implementing a generic from an str. And the reason why we did that, and this took us a little bit of work to actually figure it out, is that basically this from string is meant to be used in a way that you don't need to retain any reference to the original string. So you are basically saying, I'm going to parse something from a string, but my result is not going to keep any reference to the original string, which is not what we want to do here. Here we actually want to convert an str to an instruction that will keep a reference to that original string. So we are implementing the more generic trait from, and we need to specify all these lifetimes. Now, I hope that all of that makes sense, but feel free to ask questions here in the live stream or in the YouTube chat, in the YouTube comments if you're looking at the recording. Now, at that point, the only difference is that when we create an instruction, we can just reference the string slice. We don't need to do a string from anymore. Also, we are cheating a little bit because, of course, this might fail, but we are not implementing it in a fallible way anymore just because we know the input is actually well formatted, it's not going to fail. So we have a panic here just in case, but in reality, we know that with our input, this is not going to happen. So we also remove the OK and OK here, and we're just going to return the instruction straight away. So that was the main change. And now, since we are implementing from, we can just use x.into, and that's gonna immediately convert a given line into the equivalent instruction for that line. So if you don't remember that, I think we mentioned it in one of the previous episodes, but when you implement from, if you have a type that can be converted from one type to another, because it implements this from, like here we are saying, a generic string slice can be converted to an instruction, then you can, wherever you have a context where you need an instruction, if you have a string slice, you can just say that string slice into. So the type inference of Rust is going to figure out X is a string slice. You want to convert it to the type that is actually expected here. So this is how into works. So if you do implement from, you get the ability to use into. Everything else, I think, is just formatting. Right. Another thing, so this is just the code change, and we are going to be merging this shortly, but I think Roberto wants to add something cool about this work that he did.
Yes, to get an idea of how much this was changing the code, if it was going faster or slower, and if this was going to change stuff in any, obviously, if you don't allocate memory, it's going to be faster. By intuition, you can think about it, but where is the time spent after that? So basically, we will show how to do frame graph for Rust in one of the next episodes, but we just created a couple of frame graph with the code that was in main with the string from, so with all the allocation of the strings, and the other one with just the code for this PR that is just with the reference to str and like Luciano showed. And in the end, as you can see, there are two big blocks in the first image. There are two big blocks above X4 part 1 on the left that are the allocation of stuff. That have on top of them, again, the parsing and everything else, because you still have to do the parsing. The only difference is that instead of allocating the result, you have references to the result. So all the computational time is still needed. You get rid of a chunk of stuff that are the pieces that allocate memory. And you can have an idea of the fact that the new implementation is faster, because if you look on the right, there is that, I don't know if I can read it.
Let me try to make this a little bit bigger, maybe.
There is a hash map KVSA insert
this
on
guy,
the right. Yeah, that guy on the right. Okay, that guy on the right, that piece of code didn't change it. So it was of a certain size before. It is the same size in the next image. But if you see in the next image, it is bigger because the total time went down. So obviously the two images are wide in the same way, but the second one is taking less time. So you are more zoomed in basically in the image, and so you see that on the left we have a bunch of stuff that are missing. We are using dot from now, no more the string stuff and the from str, sorry. And in this way you can see that it's faster. You can see that it's faster, but how faster it is, we have other comments in the PR.
There you go. So there is this one first.
Yeah, that is a chain. That is a test that I did on my local machine with the branch in main and this PR. So my machine, the gain is around 28, to be honest, % of gain. If we go slightly down, there are other comments. Okay. We used Valgrind to have an idea of how faster is this solution. Basically, Valgrind used like this is counting the number of CPU instruction that we are doing. So it's not exactly a very, it's not exactly that if you use less instruction, you are faster. It's not always true, because you can have allocate, you can have CISC instruction that are slower, but they are less. But okay, but in general, it's a good hint. If you run less instruction on a CPU, the program is faster. You can go out with this. And if we take a look, this is running on all the exercises, obviously not just the one touched by the PR, but if we scroll down to our 14, yes, all the other fluctuation in the other exercise are noise. There are a couple. It's interesting that there are a couple of the 5 and the 9 exercises that they are very noisy in these regards. We will explain why in one of the next episodes. But if you see,
my assumption there is that maybe in the CI we ended up running different versions of Rust, so maybe it's optimizing a little bit less or different instructions. I don't know.
I try to keep the version the same, everything always the same. The machine of the CI is the same step, but again, being on a CI tool in a virtual machine is strange. But the good stuff of Valgrind is that it's counting the instructions. So even if the virtual machine is faster or slower, you don't care, because the number of instructions are the important factor. Then it doesn't take in account the time that it takes to run the instruction. So basically 7.23 less instruction machine code, so less instruction for the new approach. That is a lot. Probably the time on my machine, the time has a higher percentage of gain, because it also takes in account the real time of calling the kernel to get the memory, having the memory back, and stuff like that. If we scroll again, there is also the cargo benchmark. Can you scroll a little bit?
Yes, sorry, I was answering in the chat. There you go.
Here we have, okay, exercise 13, part 2 is getting slower. This is noise in our GitHub Action tester. This is what we were talking about before. Cargo bench, sadly, is running on this virtual CPU of this probably Docker container somewhere in Azure that GitHub is running, so we don't have control on that. So comparing main to PR, even if it's the same machine, even if it's the same Docker, in different moments, it means that you can have different virtual CPU allocated to you. So exercise 13, part 2, that is not touched at all, got slower of 6%. That is a lot. So it's a very noisy way of doing tests in a CI with Cargo Bench. But again, exercise 14, part 1 got faster, even if everything else got slower. So, long story short, Cargo Bench in a CI tool, that it can be Jenkins or whatever, if it's virtualized, it's not going to work, because you can't predict the CPU of a virtualized ecosystem. If you're running on bare metal and you're bare metal, okay, at that point, CI with the Cargo Bench can be considered a good measure of performances. What you can do is using Valgrind, like we did, to have an idea of the number of instructions. So basically, this is the proof that this PR is faster than the other.
Yeah, because we have both execution time and number of instructions being reduced.
Number of instruction, execution, in remote and in local, everything is telling us this is faster. So this is faster.
Right. I also remember that there was another small change we did to avoid allocation that I didn't highlight here. And it is very small, but I think the impact is actually significant. So here we were calling collect in the first implementation, which basically means get every single line from the input. Every line is going to become an instruction, and then put all of that stuff into a vector, which in reality we don't really need, because we end up processing every single instruction in a kind of stream fashion, because we just get the first instruction, we use it, we move to the second one, we use it, and so on. So at the end of the day, we did change this to just create, let's say, an iterator. Probably it's not the right terminology, but basically this is kind of a lazy structure. It's not collecting everything straight away. and then we just leave the for exactly as it is, and that for is going to consume the data basically on the fly. So we could avoid the allocation coming from collect this way. And I think that's another thing that we can see here where, let me
open the other
see.
image. Yeah.
Is this?
This one.
Okay, this is the old one. And I think you see here that we are allocating a vector T. And here we don't have that allocation anymore. So this one is a little bit flatter because we are not storing all the instructions up front just to iterate over them again. So I think that was another small change, but did have some level of impact. And it's interesting that in Rust you can just avoid to call collect, and you get something that you can use a for loop exactly in the same way. So you still get two things that are iterable. In one case, you are pre-allocating everything. In the other case, you get the data as you go.
Yeah, the only problem, if you have to use again the data, you don't have them anymore. But in this case, we don't have to use that vector anymore. Instead, there are other exercises, for example, the 13 with the buses, that we need to go over the vector multiple times. So it's not possible to not call collect. Otherwise, you have to recompute the vector every time, and is getting to slower than allocating stuff and keeping them there.
All right, so I'm going to merge this one, pull, and then we can continue from here in part 2. And thank you, Roberto, for doing all this amazing work about performance. I think it's going to really be worth a dedicated episode.
Yeah, if somebody wants to take a look at how we do this, there are in the repository, if you want to show them, there is a folder called GitHub something, GitHub Workflows. Right? Yeah, there is the Rust one that is running the test, the PR benchmark that is running a cargo bench, and the Valgrind that is running Valgrind.
Yeah, we'll probably be spending some time in a dedicated episode.
Yeah, probably we will do a dedicated episode.
So let me share my IDE now, if I can. There you go. Okay, so now that we did part 1, by the way, if you don't remember part 1 or you haven't seen the videos, the main idea was essentially that it's like something like a simulation of a CPU or something with a memory, and you get these instructions that allow you to change the memory in different locations. And the way that you do that is that you have a mask, and then you basically say at memory 8, position 8 in memory, apply 11 with this mask. So instructions can be of type mask, which means set the current mask, or memory allocations, where you have a value to apply to a particular reference and the mask that is currently set. Now, there are rules on how to apply this mask to this current number. I'm not going to explain all of them because these rules change in the part 2. So let's just see how they change in part 2. Okay, so essentially in part 2, these are the rules. So basically you will have instructions, mask equals something that sets the current mask. At some point you have assign this value with the mask applied somehow to this position. How is that going to be interpreted by version 2 of our program, which is the one that we need to write? And the way we need to interpret that is basically you take the bit mask and you take this number and you expand this number. You take the address
in this part.
Do you take the address? Yes, you don't
change the value. In the part 1, you change the value. In part 2, you change the address.
In the part 2, you change the address. So you need to take this number as a binary string, and basically bit by bit, you need to apply the mask here. And let's see what are the rules. So if in the bit mask, the current bit is 0, that means that whatever you have in the current position at the same bit, it's unchanged. If you have 1, that means that you have to override. So if you have 1 in the mask, it means that doesn't matter anymore the value you have in the address is going to be set to 1. So you're going to override. Now, if you have x, which is a special value that you can see here, sometime happens. So this is like a, not really a regular bit mask, it's like, yeah, an extension of a bit mask if you want, with the special value x. And x basically means that the current value in the address is going to be floating. And floating essentially means that it could be either a 1 or a 0. So we don't really know in advance, which essentially means that we need to compute all the potential values that are generated by using all the possible 1s or 0s in every x. And that will give us not just one address, but it will give us potentially multiple addresses. So we will need to set all the addresses that came out this way. I think if I show an example, it's going to be easier to understand. For instance, we have an example here, which is essentially applying these first two instructions. The first one will set this mask. The second one is going to say mem42 equal 100. So we need to take the current address and apply the mask to figure out all the addresses that we need to set to 100. And the way we do that is this. So this is the address, which is 42 in a binary visualization, right? Then we apply the mask, and the mask says every time it's 0, it's unchanged. And here the mask is always 0, so everything remains 0. Other zeros, oh, this is the address, so we need to look at the mask. So other zeros here remain unchanged. So 1, 0 remains 1, 0 here. When you have a 1, that it's overridden, so that even if it's 0 here, it becomes 1. Here it's 1, it was 1 even here, but at the end of the day, it needs to become 1. When you have x's, for now they stay x's, but we will need to expand all the potential values from here. I hope all of that makes sense. It took me a while to actually understand it. But how do you expand these two values? You expand them by essentially using all the possible values you have here. This can be 0 and 1, this can be 0 and 1. So at the end of the day, we have 4 combinations. And if you try to expand all these 4 combinations, you get 4 values. This one, this one, this one, and this one. And you get 26, 27, 58, and 59. So that basically means that this instruction means take the 4 values that are coming up by applying the mask here. So take 26, 27, and so on, and assign all of that to 100. Make sense, Roberto?
Yeah.
I hope I am explaining it clearly. Feel free to ask questions. Okay.
Then there is another example that is now with 3 axes.
Yeah. And the interesting thing you can see from here that you are getting 8 combinations. So of course, since every single digit can only have 2 values, either 1 or 0, then of course, if you have 3 x's, the total amount of combinations you can have is 2 elevated power of the number of x's. So if you do 2 power of 3, basically you get 8 combinations. So this is probably something we'll need to use in our implementation because we'll need to figure out a way to generate all the possible combinations.
Yeah, if you take a look, just to point out, we have 26 and 27 here. That overlap, if you scroll up, they overlap with the previous instruction. No, a little bit, another 2 lines up. Yeah, 26 and 27, if you see, they overlap with the previous command. So the value will be overwritten by this one. So for this, at the beginning, we thought of somebody can think of, no, I'm not computing all the possible values. I use the mask, the bit mask that come out as key of our hash map. The problem in doing that is that some maps, some bit masks are going to work on the same memory slots. So you have to really simulate all of them and write in all of them. Otherwise, you are missing some overwrite. And if you don't overwrite a 100 with a, what is the other number of the second instruction? 1. If you don't overwrite 100 with 1, obviously the result at the end of the day is wrong. So
Yep, I did. Let me stop sharing and share another window where I try to explain the idea in a different way, and I hope it's going to be a little bit more visual what we need to do.
Yeah, so also remember that we always start with a solution that works. Then when we have green tests, we refactor. But yeah, just to be sure that we are not breaking stuff trying to refactor.
Yeah, so essentially now the complexity is mostly on how do we compute the addresses list for a given starting address and the mask, right? So we have all the rules, and at the end of the day, we end up with a bit string, let's call it bit string, or a string if you want, where you have zeros, ones, and x's. And we need to expand this string to get the list of all the addresses that we need to mutate for the current instruction. So the way I try to visualize this, and this is the same example we were seeing before with 3 x's, is that we have 8 addresses that are going to come out of this, because of course, again, 2 to the power of 3 is going to give us 8 possibilities here. So the way that I wanted to visualize this is, okay, we will have 8 numbers, and in these 8 numbers, there are placeholders that we will need to fill with all the possible combinations of 1 and zeros, right? And then once we replace here all the 1s and zeros, we will have 8 numbers that are the memory addresses that we need to assign. So the interesting thing, and this took me a while to understand, even if it's probably trivial for people that deal with binary stuff frequently, like Roberto, is that like the easiest way to do that is essentially to enumerate all the numbers from 0 to 7 and then look at their binary representation. So if you start from 0 and go to 7, you have 000, 001, and so on. And these are the numbers that you need to put in the placeholders. Now, the complexity here, and we will need to figure out a nice way to do that, is that you cannot just like bit mask them, because of course those might be in positions far away from each other. So you will need to place them in the right slot. So we'll see what's the best way to do that. Maybe we'll come up with a solution that is not really the best, and then we optimize. But yeah, that will be the next challenge. How do we spread all this value in the right placeholders? So I think this is what we want to do. Let's just keep in mind this idea. For me, was very visual way to understand the problem. Okay, so I think it's time to do some code, otherwise people will fall asleep. So let me share again the editor. Now you can see me stumbling with the keyboard. Okay, so let's go to our implementation and we go to part 2, which, I mean, is still a placeholder. Now I think we can copy all the parsing because that's going to be exactly
well, line 25 and the map of the memory. Yeah, those two are fine. We also need the OR mask because we have to set bits to 1, and that was done with the OR mask. So we can copy the declaration of the OR mask. We don't need the end line 30, sorry. The end mask is not needed anymore because the rule, the rule for the 0 changed. Now 0 is doing nothing, so we don't care about the end mask.
Exactly.
The 1 is still setting to 1, so we still need the OR mask.
Okay, so why is it complaining here? Up.
Cannot infer the type because we still have to write code.
Okay.
It will infer the type when we have the loop, probably.
Which is something we can do now, right? Because
yeah, for instruction in how it was. You can copy it because it's also
let's copy instruction in instead.
Yeah, then we have the match that again we need the match too.
Exactly.
So yeah, probably when this is done and the two tests are green, we could do refactor and having shared the code, but not now. Now we are copy and pasting. Yay.
And mem.
Not mem, not mask.
And mem has 2 values, which is the address and the value we are trying to assign that we just call key and value here.
You can call them address and value, key and value.
Yeah, probably address makes more sense now that we're explaining the problem this way.
I'm not strongly opinionated on that.
Okay, so
now when we have a mask, we have to compute two stuff. We have to compute the or mask like before. So if the bit is a 1, we have to store a 1. That we can exactly copy the code from above.
So let's do all of that. So or mask, let's copy everything and then
then remove the end mask, and also we have to add the floating bits handling.
I don't know why this is complaining. Let me add also all of this, and at that point will be exactly the same. Maybe I should have copy pasted everything and then changed.
And then removing stuff. Don't know.
Because this will be also the same. Like once all the memory is set, we should be able to return. Let's see what I'm doing wrong. I'm not returning. I am.
No, well, there is end mask that is not declared, and we are using. Let's try to remove end mask. And, okay, you can remove line 65 because we don't need it. Yeah, we can remove that line 65. You can remove the if at 71. To all the if.
All the if, yes.
Yeah, go home. Now still complaining. Why?
Why is it still complaining? Expected U64 found unit value. Is it returning all of this? Why? Shouldn't. Close parenthesis where? So this one. Oh, yes, this one.
We missed the... okay, we missed
Good suggestion. Thank you, Tommaso. You are an eagle eye somehow.
Yeah.
Okay, here a key is not the same, but we'll change that later.
That's like, okay, later. Let's focus on the mask. Now the mask, when it's a 1, we still have to set the bit to 1. So still like before, we populate our mask. If it is a X, we have to remember that this position, the position that we are in, we must store it somewhere. And we must remember that it must be the floating bit, like they call it. So we can have a vector of...
U sides, I guess.
U sides, yeah, okay, a vector of U sides. Basically, we have to store number between 0 and 35 because they are the bit. So, yeah, weight was enough, but probably U size is better, so you avoid the problems with... give a name to the variable because let mutable vec size is fine, but floating bits. I think in the README they call it in the exercise they call it floating bits. So yeah, floating bits is a good name.
So basically, what we want to do, else if c is equal x, then in this case, what we want to do is floating bits dot push. And the current.
We need to enumerate to know what is the current index. Also, is 35 minus the current index because we start from left and we go to right. So
we need I guess, and C.
Oh yeah. I is the universal character for an index. No, it's not happy.
I think we need to do that. Okay, now
double equal in that line 71. Okay.
And here we need to push 35
minus I. Yes.
Because we
start from left because as the strings, the mask is a string, so it starts left to right, not right to left, because obviously we write a number in the other direction respect to how we write text. So yes, we start with index 0, but the one at index 0 is the bit at number 35. So we have to write 35. When we move over to the 35th character, that is bit 0. So we have to do 35 minus I. And in that way, we also have to reset the floating bits to empty before, when we do our mask 0 in line 66, we have to set that to an empty vector. So I don't know.
I think we can do clear for that.
Clear?
Let's see if that's true. Yeah, clears the vector, removing all values.
Okay. So now in our loop, when we find a mask, we prepare the two variables that we need to apply in the mem instruction that are the
by the way,
mask.
one quick thing I'm realizing is that if we do vec new, we can probably give it a capacity, right? Which we know the capacity is never going to be bigger than
36.
35.
It's 36,
36.
because it's 0 to 35 is 36 bits.
Is that how it's done?
To set a capacity?
Oh no, I think it's vec with capacity. There you go. Okay.
Yeah,
so we're never going to reallocate the vector.
Yeah, the vector is always the set amount of bits at maximum, because if they are all x's, if we have just one x, will be one value, but capacity is giving you the
maximum size.
Yeah, sorry.
So it's allocated once and then never moved in memory.
Yeah, probably it's fast. We can also try to not do that later and see the difference. Let's go to mem at this point. Here, like you said before, is the tricky part, because we have a base address that our base address is address or the OR mask, because remember that we have to set, our base address is that. We have to set the bit to 1 to follow the rules.
And we take
other or the binary or the pipe, with the OR mask. That will give a number. Let's see if the types is happy with the types.
Yeah.
Okay, he's happy with the types.
And now this doesn't make sense anymore, because we'll need to do this multiple times, expanding on the access.
With only val, we don't have to do anything to the right side. We have to do changes to the left side, to our, how we call it, address. So now we already say that if we have two x's, we have to do that 4 times. If we have 3 x's, we have to do that 8 times. If we have 36 x's, we have to do that 2 to the power of 36. So basically, we have to do that 2 to the power of the length of a floating base.
Yeah, it's 2 power of num x, basically.
Yeah, number of x's. That is the length of our floating base vector. So we can do a loop on top of that. So numeric loop.
Yeah, I suppose we can do that as for I in 0 to power of floating bits.
Floating bits length. How do you take the length?
Length, I think.
Okay, that is an E32, but again, we need an E64, so you can do 2 underline O64.
Yes, good point.
Yeah, to cast everything to 60. Now he's complaining.
And this one we need to do as U64. Or use POV I think was a suggestion we got last time. Let's see if that works. No?
Complaining because
no name. And if we just do POV, oh, it needs to be as U32. Okay.
Cool. Okay, I accept it. We are working with 36 bits, so we have to use U64 because of that, like the other time. So inside here now we have a base address. We know what are the bits to set to different values. We have I, that is the current iteration of those values that we have to replace. So the bits that are in I are the bits that must be set in the current iteration of our loop over the base address. So we have to compute the final address. How do we want to call this final address?
Yeah, let's call it final address.
That is mutable again, because we have to set a bit up and down. So final address start as the base address.
But we don't need to clone, I suppose, because it's
no, those are integers, so you don't have to clone integers, I think.
Okay.
Cool. Now, for all the bits that we have to change into floating bits, keeping track. Do we have to keep track of what bit is it?
We need to keep track of the position right?
We have to, okay, now we have an array of positions. We have to keep track if, for example, if we have 3 numbers that mean that we had 3 axes, we have to have a tuple of 0 at position 5, 1 at position 7, 2 at position, I don't know, 31. And we have to take the bit 0 of our I, that is our counter, and put it in position 7. We have to take a bit 1 of I and put it in position 9 of the final address. We have to take the bit 2 of I and put it in position 31 of final address. So we have to do this mapping of bits.
Exactly.
Distribute them.
So we need to iterate over all the floating bits at this point,
yeah,
right?
It would on the enumerate of the floating bit, because we also need the from bit to bit.
So how do we call this? We call it B, I guess.
But you can call it from bit to bit, because the first one will be the from bit. So bit 0 of I, bit 1 of I, and the second one will be to the bit n of final address.
Yeah, and this is gonna be floating bits.
Floating bits dot enumerate. Floating bits dot enumerate.
Enumerate. Yes. Oh, either.
Ah, okay. We have to iter, then enumerate. Okay. We have to
because
keep
it's a vector at that point.
Yeah, it's a vector. We can't destroy the vector because we have to use the vector multiple times. If we have multiple mem instruction, that vector will be used multiple times, so we can't destroy it after just one run. We have to keep it. At this point, if we have to copy the bit, so what do we do? If the bit is 0, we have to set the bit at 0 in the right position. If the bit is 1, we have to set the bit to 1 in the right position. So at this point, we can do if I and the binary end, not the open round brackets. 1 double lesser. Yeah, we have to shift the bit by from bit.
From bit. Okay. I'm grasping this.
This instruction is telling us if the bit in I in position from bit is 1. So if this bit is 1, we have to set the bit to 1 in the corresponding 2-bit position of the final address. So final address will be or equal the final address.
One thing I want to clarify, because this took me a while to figure out, and spoiler, I did check this a little bit in advance, and still I am barely understanding it. But the idea is that this one creates a number that is just 1. So it's like all zeros on the left and 1 on the right. Then when you shift, you are basically moving that 1 by the number of bits that you have here. And then at that point, you are doing an AND between this number and the number that results from that 1 being moved. Make sense, Roberto? Am I explaining it well? Okay.
So basically, you are checking if the bit from bit of I is 1, because if it is 1, it will not be 0. And if in Rust, do we have to be explicit about the types? So we have to say different from 0, or is fine?
I think not. I think it should be fine. Let's see what is it complaining about.
Okay.
No, we need to say different than 0, right?
From 0, yeah. Okay, at this point.
Makes sense. Because otherwise this is just going to be an expression evaluated into a number, and the if is expecting.
Yeah, because obviously if you work in C, a number is true and 0 is false. So, but here we are not in C.
Which is good, I suppose. It's better to be explicit.
Okay, let's go back inside our, Here we have to take final address and change the bit in position 2-bit. So final address or the pipe equal, or equal.
Yes.
This is doing a bit or on top of final address of what?
So this is basically like final address
or
pipe.
Something. Yeah, open bracket, round brackets. 1 shifted again left of 2-bit, because now we have to shift by where we want to put it.
Yeah, so basically this from bit and to bit, they are not the values of the bits, but the position in the number.
So we have to compute, do the shift, moving the bit where it's needed. Semicolon. Now, instead, if it is 1.
So if it is 1.
No, if it is 0, sorry. No, here we are in the, sorry. The first if is, if the bit is 1, because that's different from 0 is fine. Now in the else of this, okay, in the else, we have to set the bit to 0. Because if the bit is 0, we have to copy the 0 to the final position. But
yeah, so do we just keep an else, or is there any other condition?
No. Oh, okay. I'm explaining. We have to put the bit to 0. But how do you do that? You have to do an AND with a number made of 36 bits, but where the 0 in position 2-bit is a 0. So basically a very big sequence of 1, a 0 somewhere that we have to move around, and again enough ones to arrive to 36 bits. This is tricky. Basically it's a NOT, so you have to do a NOT of a 1 moved by 2-bit, but we are working with 64 bits, not with 36 bits. Yeah, it's tricky. We can try, but probably we can change it later. So open just the curly brackets. Right. So now we have to set the bit. So now our final address is.
I'm keeping the extended syntax just for clarity, and then we can.
So we have to make a bit 0. So we have to do an AND. This is how you make a bit 0. Now we have to do this AND against what? Against 1 shifted of 2-bit again.
2-bit, yes.
This stuff must be put a binary NOT in front of it. What is binary the symbol for the binary NOT in Rust? In Python is no, before the round brackets.
Yeah. Might be a tilde as well. Let's see what happens.
Is a tilde also in yeah, okay. Now put no, but it's not ended. No, okay. Ah no, it's a exclamation mark. Okay, this is the bitwise. Okay, now it's complaining about something. What types?
This is just a warning. Well, let's check it out later.
Okay, but it's not ended there, because here we are doing a NOT on 64 bits. No good. We have to do a NOT on 36 bits, because our specifications say that our machine is a 36 bit machine. So we have to put our round brackets around the NOT and this. Yeah. We have to do an AND. With no, even in the end, the end is commutative, is not important. AND. Oh, let me wait a moment. No, it's fine. We don't need it because the bits are already 0. No, you're right. We don't need it because we start with numbers that can't be greater than 36 bits. Right. No, let's go on. So yeah.
By the way, I want to do a quick pause because we just got raided. So thank you, Brooke Zerger, for the raid. With everyone watching, what we are doing is trying to solve Advent of Code challenges in Rust. So we can also have an excuse to learn some Rust. And feel free to check out our recordings on YouTube, which you can find the link on the info section. And also check out our repository where we have all the previous solutions here. Now, today we are just solving a specific exercise. So you are just deep in the weeds of ourselves, trying to figure out the bit logic that we need to use to manipulate bits. So yeah, sorry if that's not super clear right now, but bear with us. We'll do a checkup at the end. We'll try to go over again the idea and explain it better.
So, Luciano, I think that the second N is not needed. It's just a safeguard. Probably we don't need. If the test is read, we will add it. So now, inside this loop, So between line 88 and 89, inside the outer loop, sorry. So out of this loop, we have final. Yeah. Out of the loop, we have final address that is the final address. So we have to do mem insert in the final address. So we copy
this guy, right? And this time we use, rather than key, we use final address.
And on the right, we just use val because.
And on the right, we just use val because we already computed. Well, we don't need to compute that.
No, we don't have to touch val in the second part.
Let's see what
he's complaining about. Manual implementation of a sign. Okay, it say that you can do or equal.
Fair enough. I mean, I don't mind this one as it is. Also, we can use, now that we explained the idea, we can just use this and this, right?
Yeah, it probably
which is a little bit more succinct, but it's still going to complain, I guess. Here we don't need the parentheses anymore, right?
Okay, well.
And it's not complaining anymore because now I suppose Clippy doesn't understand anymore that these are assignments. Yeah, fair enough. Let's keep it this way. I think it's more readable.
Okay, said so. We still have the instruction that sum everything at the end of the functions?
Yes.
Okay.
So I think we can just run the test, right?
Yeah, we can try and hope that we don't have an error. Or if we have, we'll find out why. Yeah, that the end is probably going to work even without that. Yeah. Let's see. Okay.
Yeah, it works. Nice.
Yay.
Good job. Also, the kids outside your windows are happy.
Sorry, guys. Kids are playing. It's not raining enough.
Okay,
it's like raining, but for an Irish kid, it's not enough to go inside.
Let's. What do we do? Do we want to do another recap explaining the whole idea, or try something else?
Let's see if we can optimize something like I said before. Now there are parts that we can make common between part 1 and part 2.
Mm-hmm.
For example, the parsing of the instructions.
Fair enough.
The parsing of the mask can be common. I explain you why. In the first part, the mask is giving you an AND mask and a NOR mask. In the second part, is giving you a NOR mask and a floating bit. Is enough to create a function that give you back an AND mask, a NOR mask, and a floating bit. And in the part 1, you just use OR mask and then mask. In part 2, you use OR mask and the floating bit. And when you unpack the 3 values, you put an underline where you don't need the value. That, in my opinion, is not that.
Okay, we can try that. It might be interesting to see if we need references and stuff like that, but let's do that. I think it's a good idea.
To kill us. Okay. So basically, it's a function that from a string give you back 3 values that are 2u64 and the vector of u sizes. Okay.
Yeah. So what do we call it? Parse mask.
Parse mask, yeah, is what it's doing.
And we receive a mask, which is an str.
Receive an instruction of type mask.
Right.
No, we receive. Well, yes, we can get the string. You are right. Yes, and we give back
a tuple where we have u64, and a vec of u size.
If we can do that. Yes. When I have 3 parameters that I return instead of 2, I always think if the best stuff is not giving a tuple back, but creating a structure and give back the structure. I'm always
do that.
I'm always puzzled by this.
I agree again, by the way. It will be a lot clearer if we have names
because basically with the tuple you lose the names. And so you lose the semantic of what you are giving back. Keeping it in a structure, you keep the semantic of what you are giving back. But I never know when he's overkill or when he's fine. I mean, obviously you are taking more time doing this, but this is more readable.
And then we have floating bits.
Yeah.
right? So now this guy is going to return a mask.
A mask part, or yeah, parsed mask parts, something. The code you can take.
We have the or mask and end mask there, right?
Oh, but no, because now you need you don't need them because that was needed the very. But well, that is not needed. Remove it.
Which one?
Yeah, those 2 lines, they're not needed.
Oh, because you want to do them all in one go?
Remove it.
Cool.
Go down, copy from line 44.
From line 44.
Yeah, the content of that match. That is line 44 to there. Okay.
Yes.
Cool.
But
now
we need to do
yeah, we have to do all the stuff.
Right, and then at the end we can do mask parts of this, and we already have end mask and or mask.
Now we have to, yeah, our mask is the first. You see, you switch at them. Now having the names is easy to get it. If it was a tuple, you were switching them, then you were messing up everything.
I'm gonna create the floating bits as well, so it doesn't combine anymore.
You can go and copy the code from the second part, or you can write it
faster this way. Actually, now we can do back with
the new width side capacity,
36, right?
36, yeah.
And this guy is gonna be here, and now all of it should work.
But we have to populate.
We are not doing anything around this. So let's
go to take the code from part 2. You can take the code that is,
which is this one, right?
That if, yeah.
So this is gonna go inside here.
Without the else is fine. I mean,
fair enough. I suppose we should put the else everywhere, right? If we want to
no.
Oh no, this one, yes. I remember why we had this conversation.
Yeah, we already had this conversation. Okay, you can put this. You can put this in else with the first if, because if it is one.
Sorry, I copied it in the wrong place. I am.
If it is one, do this. Else, if it is x, do the top. Okay.
Yeah.
No. Okay.
Now I is gonna be what? Sorry.
You can put this in the else of the first if, because it said if c is 1, else if c is x, do your stuff. Then 41 is a completely different topic that we discussed last time, because you're saying c different from 0, that is mentioned 2 different cases. So you can leave it like it is now, or you can put this in else with the first if, like you want.
Yes, we can put this with.
Probably it's more readable like this. Probably.
Yeah, leave it like this. I think it's best. We need to do the enumerate, right?
Yeah,
because we need the I.
Exactly.
And now we have I and C. And now all should work.
Okay, now it's complaining about parse mask that is never used.
That we are not using it, yes, of course.
Let's go to use it. So now
in the first
in
part one,
yeah,
you can just say let part. Actually, we can probably destructure here and not.
We can destructure. I have no idea.
Let's do this first. Parts equal parts mask of mask. And now with this one, we should have all the parts.
Yeah,
I'm just curious to see if we can do this and mask or
the
mask.
First one is the end of the or. You never remember. And underline.
Shouldn't matter, right? No, we cannot do that.
No.
Oh, maybe we can do that if we do
round brackets.
No. Mask parts, maybe. With parentheses. I don't know. There might be a way to do that, the structuring that we want to do. If anyone knows in the chat.
But this is not JavaScript, so you don't know how.
Yeah. So okay, let's keep the parts as they are. Mask parts.
Yeah, at this point you can say that end mask is mask parts dot end mask.
We can remove all of this, right?
Yeah, but you have to assign. Or do you want to use them directly?
No, we can use mask parts dot end mask and or mask.
Yeah, at this point, but
right?
you have to at this point you have to declare it mutable in line 62 because
in line 62 we can remove these guys. Or not?
and yeah, but mask parts must be declared there.
Yes.
And mutated in line 66.
So this will be mute and mutated in line 66.
67, 65 now. Remove the let.
Yes, okay. Okay.
And I don't think
we can remove all of that, right?
Yeah. I don't think okay, remove it.
That 61 will work because we
okay. Yeah, you have to initialize, declare it, but not initialize to anything, or initialize to like we were doing before, to a structure with 0, the max int that we computed, and an empty vector.
Yes, which basically is going to be something like this repeated 36 times. Right?
An X repeated 36 times. That is the do nothing.
I'm curious if you can do repeat, yes, 36.
Yeah, okay. Cool. This is the useless.
Is this giving us a string? Okay, then let's do
SRF. Okay. Now in line 68 we have to use mask part dot end mask and mask part dot or mask. Because yeah, otherwise it doesn't know the variables anymore. In theory, try the test, but
we can run the tests. Yes.
Yeah, this is a refactor that keep the test green. Okay, except that it's throwing a warning. What was?
Yeah, because there is something we are not using. We are never using the floated bits from that struct because we need to do the changes.
We use it only in exercise 2.
Mm-hmm.
Now
we can refactor exercise 2.
Yeah, the matching for mask is the same.
The matching for mask is the same. So we need to do the same thing here. So basically we need to copy all the stuff.
Yeah, line 61. Instead of 80 and 81.
Here.
Yeah, 80, 81 and 82.
This guy and this guy, yes.
They go away, perfect.
And now here we do the same stuff. Mask parts.
Yeah, one line of code instead of multiple copy and pasted between 85 and 94.
Right.
Away,
yes.
Track. Now we have to do.
Now this guy becomes mask parts dot or mask floating bits same and floating bits same. And that should be it.
Try again if it's still green. Okay, now he's not even complaining anymore. Cool. Do you want to make a comment here?
Yes, I like that Rust, when you create structs and then you have parts of the struct that you are never using, is able to spot that and warn you.
Yeah, it is able to spot that we never use the vector, even if we use the struct in the end. So try do a commit just to keep track of where we are.
You're not going to see my other screen, but I'm doing a commit, trust me.
Or you can open a terminal in VS Code.
No, I am afraid of that.
Oh my God.
So solve exercise 2020-14. Year 2020, exercise 14, part 2. Okay, so what else can we do? Do we leave it at that for today, or
we can take a look? What are the part of the code that are exactly the same? From line 84 and 86 in the two parts are exactly the same.
84 and 86, yes, but here it will be a bit tricky because yeah.
Okay, what if this was Python? Sorry if I always do this. If this was Python, I would make a context manager changing the code that is inside, that is mem, that is doing stuff. Or I will do a function that take another function as parameter. So the function is doing for instruction, match instruction, do your stuff. Match mem, call the closure that I gave you for mem. So I will generalize with a function that take another function as parameter and is running that function every time there is a mem instruction, and is keeping the mask and the for loop in the common shared code. So at that point, you just have that parsing in one place that we already have because we have the parse mask function. But also the logic of the match when it's a mask called the function is in only one place, not in two places like now. I don't remember if it's easy or not passing function as parameters in Rust. I remember there was some tricky stuff around the type that we had to use lazy static.
Or no, there are some trick things that probably we can leave it for next time. I like one suggestion we got here from Tommaso. I'm going to put it on screen because I think this is something we keep forgetting, and it's probably the more idiomatic way to do this thing in Rust.
Also, this is for real from string, because we are getting a string and we are giving back something that is completely different, that are two integers and a vector of usides. We are not keeping reference to the string, so it's not a from, it's for real from string. So, and every time we forget that this exists.
By the way, thank you, Christoph. We got another raid. Ooh, 32 viewers. Nice. Let's wait a few seconds and then we're going to explain again what we do. Thanks again, Christoph.
Do you want to...
I will do this change because it should be very quick to do the impl rather than parse.
Okay, yeah, okay, let's do that.
So let's see.
I was thinking, is this going to impact the performances of part 1? We have a benchmark covering part 1, right?
We have a benchmark covering part 1. Yes.
Do we want to try to see if there are differences between main and this? Or it's not important?
I mean, when we commit, the CI is going to run, right?
Yeah, it's true. When we commit the CI,
so we can check later.
Yeah, we can check. But instead of commit, create a PR, because the differences is for PRs, not for commits.
Ooh, I already committed.
The commits
in main. So.
Well, okay. I will take a look at the Valgrind numbers and compare by hand. It's not a problem.
Thank you.
Because Valgrind is comparing the current branch I'm running on against main. That for PR makes sense.
So we can do the change now and do a PR from those changes, and then we'll see the differences.
Yeah, we will see the difference. Okay. If you work committing directly to main, you lose this feature.
Yep. So, by the way, again, thank you, Christoph, for the raid, and for people following us, what we are doing today. And we are about to finish off, so sorry if we're not going to last long on this stream. But basically what we do, we are solving advent of code in Rust as an excuse to learn and practice Rust. Today, we are solving the exercise number 14 of year 2020, so last year's one. We did solve part 1 in the previous stream. Today, we solved part 2, and now we are just playing around to see what can we do and make it more idiomatic Rust or more optimized code. So one of the things that we always keep forgetting, and thank you to Tommaso, who is one of our most beloved followers.
And main contributor at this point.
And main contributors. He is always reminding us, guys, use the traits that Rust is giving you. Don't reinvent the wheel with new parser functions. Just implement from str. So this is what we want to do for this struct, which basically means implement from str for mask parts. And then we are going to rely on, come on.
No.
Come on. What's the signature? Yeah, today Rust, next year Haskell. Maybe not.
I tried Haskell multiple times. I can't go through. It's incredible. I tried 3 different times. I have a block. I don't know, a psychological block against it. Functional
Meanwhile, meanwhile, I'm checking what's the right syntax. So Roberto, keep going. Keep telling stories.
Keep going. Go on. Take a joke. No, I always tried with Haskell. The problem is that jumping to functional requires some effort. Jumping to a language with a approach, so a mathematical approach requires some effort. Then you put effort with effort, you have effort square, and going in effort square is a little bit too much. For example, I tried Clojure. Yeah, Clojure was, I don't want to say that it's easy, so I don't want to say that, but I didn't have a lot of problems going to Clojure. Obviously, I did the normal errors. You wrote str and not std probably up there.
No, that's the right one, I think.
It's the right one? Okay, sorry, so it's complaining.
Why it is complaining? It's not complaining anymore, but we need to implement the right function now.
Yeah, that is called...
Which, again, I'm going to copy-paste brutally, because I can never remember. And it's all of this. So we need to specify the type, and then there is a specific function. Are you happy now, Rust? What am I doing wrong? Isn't it str? It is.
std, str.
Oh, std, str, yes.
Okay.
Okay. And now this is complaining because we are not returning the right thing yet.
I was partially right.
You were right 100%. So now we can copy all of this here, and this one will be an okay of all of that. Right? Do I have too many things?
Brackets,
I
probably. Okay.
Did I break something else? That this is not called mask because
that is called this. Now we can call it mask there, yeah.
And all of this doesn't make sense anymore. And now, of course, here we need to use the right function, which is going to be, where are we doing that? Here.
Line 65 and on line 69.
So this is going to be mask.parse.unwrap. And now we need to declare the type because otherwise it doesn't know what to parse to. So this is going to be mask parse. What's going wrong now?
Are you fine with all the parentheses in?
Probably not.
Take a look.
Let's see. This one. Yeah, this one seems broken. Or not. No, this is the right for each. This
is the one in line 34 that I'm not sure. Probably you have to close an additional. Yeah, we are not closing the one from line 31.
The function.
Close there. Okay.
That should
now
be
it. Is happy.
Thank you. And now parse mask
is.
Oh yeah, this one we need to do the same stuff.
Yeah, X repeat as a str parse, or probably we can skip the as str with parse unwrap.
Let's see. I'm not sure. Let's see what happens. Okay. And why is it still complaining here?
Line 70, we are assigning on top of the
we don't need to redeclare the type.
Yeah, exactly. Copy because of laziness. At least 66, that is long.
Now I'm gonna
mask parse unwrap. Yeah, that one you can write. It is short stuff.
If I can type. Okay, that's very good. I'm gonna create a PR for this, and I think
run the test. We can check.
Ooh, you don't trust our skills. No. Let's see if you are right or not. No, you should have trusted our skills.
When you refactor, always run the test. I always run the test before refactoring and checking that they are green.
No, fair enough. Use from str in x14 p2. This is the branch. now I'm going to open a PR, and we'll be able to check the numbers in the next live stream, which probably is going to be next Monday. So make sure to subscribe the channel, and that way you can get.
Luciano, is there a way for people to ask us what they want to see next time? I mean, we are doing exercise of Advent code, and we are doing this. Cool. But now there are options that we can give to people. We can go on with coding. We can show the GitHub Action pipeline. We can talk about performances. We can show how to do flame graphs. We can show how to do cargo benches. Now that we open and all of those can take half an hour or 1 hour of discussion. So what do you think?
Yeah, I mean, there are many ways to get in touch with us. You can find our contacts in the info box on Twitch and also on YouTube if you're watching from YouTube. So feel free to get in touch with us and ask. Well, tell us your preference, which is not going to be scaling a cluster, because I have no idea how to scale a cluster in Rust. So sorry. Maybe one day we'll get there, but not yet quite there.
Scaling a cluster. You put everything in EKS and then you write a YAML. Done.
Exactly. Yeah, Roberto will tell you that. Okay, so I'm going to stop sharing, and I'm going to thank you everyone for following the stream so far. And the usual wrapping up, again, feel free to get in touch with us. Follow us on Twitter or wherever you are the most active, LinkedIn. You'll find us in the right channels. And if you're watching the recording on YouTube, we stream almost every Monday at 5 p.m. UTC. If you're watching us on Twitch, we have a YouTube channel with all the previous recordings. So this one will be there very shortly. And if you want to do a PR, because you think something can be done better or that we can explore different options, that's actually something we really, really enjoy. So feel free to do it. Again, the repository is here, if I can find, and also linked everywhere if you look at the descriptions. So definitely feel free to send us a PR. So
next time that somebody will Google Rust Advent, will find your repository, because it's spreading around the internet.
I spammed it enough on the web. So again, thank you very much, everyone. I don't know if we can do a raid. I'm going to try to do a raid as well, maybe. How do you do that from the mobile app? No idea. I'm going to do it from...
You have to buy a streaming deck, those stuff that cost like €300 with just...
Exactly. Ooh, is there an echo? No, not yet.
No, I have no echo.
That's good. So let's do a raid. Nobody's doing coding.
In a bathtub, in bikini, in
no,
a bathtub. No,
let's not do that.
So now the patron is give us €5 or we'll do that.
Oh, nobody's live now.
So let's go to dinner. What can I say?
Yeah, somebody's doing basic programming, so I think we should write them.
So they freak out and we say, "Oh my God, somebody's looking at me. What's happening?"
Okay, thanks very much again, everyone. I'll see you at the next episode. Bye.
Bye.